Put your phone in airplane mode. No signal, no Wi-Fi, nothing coming in. Now open your Authenticator app. 6 digits, sitting there, counting down. They are still the right ones. The website will accept them. Nothing was sent to your phone to produce that number, and nothing was sent from it either. So where did the number come from? Every figure in this video was measured on this laptop today, or taken from the standard that defines the thing. Where I am reasoning rather than measuring, the screen says so. One thing to clear up first. A code that arrives by text message is a completely different mechanism. That one really is sent to you. This video is about the other kind. The app kind. Google Authenticator, Authy, the one built into your password manager. 6 digits that change every 30 seconds. It has a proper name. TOTP, time-based one-time password. It is a published standard, and you can read the whole thing in an afternoon. Start with the only moment anything is actually exchanged. It is the QR code you scanned when you turn two-factor on. That square is not a picture. It is a short line of text, and this is all of it. The important part is in the middle. 20 random bytes, written out in letters and digits so a camera can read them. Your phone keeps a copy. The server keeps a copy. And then, as far as codes are concerned, they never speak again. Because from that point on, both sides have everything they need. The secret and the time. That is the entire list. Take the number of seconds since 1970. Divide by 30. Throw away the remainder. You get a counter that ticks up by 1 every 30 seconds. Your phone works out that number. So does the server. Neither of them asked the other one. They both just looked at a clock. Now the part that turns a counter into a code. Feed the counter and the secret into SHA, SHA-1. 20 bytes come out. Look at the last byte. Keep its bottom 4 bits, and you have a number from 0 to 15. Count that many bytes in. Take the 4 sitting there, read them as one number, and keep the last 6 digits. There is no randomness in that. No database lookup. No message. It is arithmetic, and it lands on the same answer every time. Written down, it is 6 lines. That is not a simplified version for a video. That is the whole function your Authenticator app runs. I wrote those 6 lines this morning, which proves nothing at all, because my code agreeing with my code is not evidence. So here's what settles it. The standard publishes its own test vectors, fixed inputs, and the exact outputs a correct implementation has to produce. Here are 4 of them running against my code. The expected column comes from the standard. The other one comes from my laptop. 18 vectors, across all 3 hash functions the standard allows. All 18 match. Not close. Identical. Then the test that matches the claim in the title. 2 separate programs, running as 2 separate processes on this machine, with no way to talk to each other. Each one gets the secret and reads the clock. Different process IDs. Same 6 digits. Nothing passed between them. Which leaves the countdown. Why 30 seconds? When the counter ticks, the input to the hash changes, and everything downstream of it changes with it. Watch what happens at the boundary. 1 second apart. 184239. Then 069006. Nothing carried over. One pair could be luck, so I measured 100,000 consecutive pairs. On average, 2 codes in a row share 0.59 digits. If they were unrelated random numbers, you would expect 0.6. Which is the whole point. The next code tells you nothing about the one on your screen right now. So 30 is a compromise. Make it shorter and a stolen code expires sooner. Make it longer and a phone with a slightly wrong clock still works. 30 seconds out in either direction and you get a different code entirely. The standard lets a server accept a neighboring window to cover this. How many is the server's choice, not your app's. That is the mechanism, and it is genuinely elegant. Here is the part that is less comfortable. 6 digits is 1 million possibilities. In security terms, that is not a big number. So I generated 1,000,000 codes on this laptop. Not 1,000,000 guesses at anybody's account, just 1,000,000 codes, to see what producing them costs. The slowest of 3 runs took just over 6 seconds. So the code itself is not hard to produce. The only thing standing between an attacker and your account is the server refusing to accept thousands of attempts. The standard says so itself. Section 7.3. Truncating the value makes a brute force attack possible, so the server needs to detect and stop them. It recommends a hard cap on the number of attempts, and it requires that the lockout works across separate login sessions. Otherwise, an attacker just opens 10 at once and divides the work. And there is a second thing, which almost nobody mentions. The last video showed that a website cannot tell you your password because it never stored one. It stored a hash, and a hash only goes one way. Your two-factor secret is not like that. The server has to compute the same code you do, so it has to have the actual secret, not a one-way version of it. A good server encrypts it, but encryption is a door that opens in both directions, and a hash is a door that does not. Somewhere in that system, the secret comes back out. You can see it in the cost. Checking a password was deliberately slowed to about 1/3 of a second. Checking your 6 digits took about 5 microseconds. Roughly 50,000 times cheaper because there is nothing to slow down. The secret is simply there. Which brings me to the limit worth knowing. A convincing fake login page asks for your password. Then it asks for your 6 digits, exactly as the real one would. It passes both straight to the real site while you are still looking at the loading spinner. It has 30 seconds to use that code. It needs about 1. Your Authenticator app cannot help with this, and the reason isn't everything we just built. It never learns which website the code is for. It only knows a secret and a clock. That specific gap is what passkeys were built to close, by tying the answer to the website asking the question. That is a whole video of its own. So, back to the phone in airplane mode. Your phone and that website were handed the same secret once, possibly years ago. Ever since, they have been reading the same clock and doing the same arithmetic. 2 strangers who agreed on a rule and then never needed to speak again. The code was never sent to your phone. It was worked out on it. If you want the other half of this, the last video takes apart how your password is stored, and I cracked 10 accounts on this laptop to show why it matters. And subscribe if you want more of these. There is one every day. Everything on screen is measured here, and I show you the code. See you tomorrow.